Hello students, welcome to this session on Relational Database Management System. My name is Ashish Jain. I am an assistant professor at the Department of Computer Applications at the Bhopal School of Social Sciences. Today, this is our second module in our series of functional dependencies. So let's begin today's session. This is a brief outline of this module. I'll start with attribute closure in functional dependencies, Armstrong's axioms, types of different Armstrong axioms, and equivalence of functional dependencies. Before we go ahead, let us now recap what actually is a functional dependency. We can define functional dependency, say A tends to B in a relation holds if the tuples having the same value attribute A also have the same value for the attribute B. Let us understand with an example. Suppose we have a table student with these values. Here we have functional dependency student number tends to student name as well as student number tends to student phone. These values are dependent on this key value which is student number. So this holds. But if we take functional dependency, say student name tends to student state, we can see that for a student with a name Ram, we have one entry of a student state as Haryana, but for the second we have the Punjab, which violates this property. So this second one does not hold. Also, there is a set of dependencies in a functional dependency. We say that it is functional dependency set, which is a set of relations such that it contains all the FDs present in that relation. For example, in this table we have different types of functional dependencies like this, and its set is known as a functional dependency set. Now we come to the first topic of this module, which is attribute closure of the functional dependencies. In short, we say it as FD. A set F plus is said to be the closure of a set F if the set of attributes are functionally dependent on the attributes of set F. Let us understand it better. It is a basic fundamental concept in database design which is used to ensure that our data consistency as well as the normalization of data by which we identify different attributes are dependent on others within the relational database schema. We can also say that the closure set of functional dependencies F is a set represented by F plus. It contains all the functional dependencies that can be inferred from capital F. Now let us see how we find the attribute closure or simply the closure of an attribute set. It has two steps. The first step is to add the elements of the attribute set to the result set, and second, add elements to the result set which are functionally determined from the result set recursively. That means we continuously check for the functional dependencies and add them to the resultant set. Let us take an example. Again, we have a relation called student in which different values are there. Here, if we talk about ID plus or the closure of the attribute ID, so it contains all those fields that can be reached using this ID number. So we have ID, obviously every attribute is a closure of itself. Then from ID we can refer to the name, we can refer to the state, age, country, all other fields because ID is a primary key here. Next we have state closure or closure of the attribute state. Here state, obviously it is a closure of itself, so we have to include here state, as well as country because country is associated with the state, not with the name, not with the age or any other component, right. So state plus or state closure contains state and country. In this way we can calculate the closure of any attribute. Now we come to a very important point, which is Armstrong axioms. These are basically set of rules that are helped to solve the problems of functional dependencies and reduce the complex dependencies using these rules. This is a fundamental concept which is useful in doing the normalization of databases, which we will be covering in the subsequent modules. So these Armstrong axioms are very sound and complete set of inference rules that are given by William W. Armstrong in 1974. These rules are used to test the logical implications of functional dependencies, and on the basis of this we can reduce complex functional dependency into more simpler terms. These axioms are very sound in generating the functional dependencies in the closure of a set of functional dependencies and is denoted as F plus. When applied to that set, it is denoted as F only. So, let us see the classification of axioms. We have Armstrong axioms in two categories. First is the basic set of axioms, and second we have the secondary set of axioms. In basic set we have the three primary axioms, that are reflexive rule, augmentation rule and transitive rule. In the secondary set we have decomposition rule, we have the union rule as well as pseudo transitivity rule. We will see them one by one. First we start with the basic inference rules, that is known as Armstrong basic axioms or simply Armstrong axioms. This before going ahead, it would be very useful to understand what an inference rule is. An inference rule is basically a set of rules or facts, we can say them as assertions, that we can apply to a set of functional dependencies in order to derive another functional dependencies that may be having the less complexity. So, we will take an example. Suppose we have three attributes x, y and z. These are the three sets of attributes of the same relation, say capital R. So, according to the first rule, which is reflexive rule, or the property is called reflexivity, which says that if y is subset of x, that means y subset equal x, then we say that x derives y, that means x tends to y. This rule is called reflexivity. That means if y is apart, the value of y is drawn from the value of x, we can say that x tends to y holds. The second property is called augmentation. Augmenting means changing something. So, if we have x tends to y, that means our reflexive rule is true. So, if we have x tends to y, then by adding same component both the sides, we say xz tends to yz. We are adding or augmenting this new variable with the existing one. So, we have xz tends to yz. This property is called augmentation rule. Next we have transitivity property, which says that if we have two FDs, first is x tends to y, second y tends to z. Here y is common in both these functional dependencies. So, together we can write it as x tends to z. We have x tends to y and y tends to z. So, we can write it as x tends to z. This is called transitivity. Now, let us take an example. Suppose we have an employee department relation in which we have these columns or attributes such as SSN number, we have F name, L name, department number and department name. Here in this example, we can see that if we can draw the first name or F name from a bigger set F name and L name together. So, we can say that F name is a subset of F name comma L name, then F name comma L name tends to F name. If you can relate it, the value of y is F name, the value of x is F name comma L name, right. So, this property is called reflexivity. This rule says that if I see F name equal to John and I see L name as Smith in some tuples, then I must also see the same value for F name John in the tuple. So, wherever we have John, we have the L name as Smith. Next property in the same table, we have augmentation rule. X tends to y implies that x of z tends to y of z. So, if we have department number tends to department name, then if we club the L name with department number, we also have the same L name with the department name. We can verify this here. Department number is 5, L name is Smith. Okay. Department name is research, L name is again Smith. So, in this way this property is verified. Next is transitivity. In the same table, if we have say another example is there, you can see it, then transitivity, x tends to y, y tends to z, then we can say that x tends to z. Here, since SSN number tends to department number and department number tends to department name, we can conclude it as SSN number tends to department name. Okay. This property is transitivity. Now, apart from this transitivity rule, there are other examples as well. Now, we come to additional rules or secondary rules of axioms. These rules are not the primary one, but they are derived from the primary axioms. The first of this rule is called union property or union rule. It says that if P tends to Q holds and P tends to R holds, then we can club them together. We can say that P tends to QR. that means P tends to Q as well as P tends to R, we can write it together as P tends to QR. Another example, if we have x tends to y, we have x tends to z, we can write it as x tends to yz. Here x is common between the two, right? So this property of combining them together is known as union property. Next we have composition. If we have P tends to Q and we have A tends to B, I can write it as PA tends to QB. The left hand side parts are combined together and the right hand side parts are combined together. So we have PA tends to QB. This is called composition. Next is decomposition. As the name suggests, this is just the opposite or the contrary of the union rule. Here we are separating the things together. So if we have functional dependencies which is P tends to QR, then we can write it as P tends to Q and P tends to R, just the opposite of the union rule. Similarly, if we have variables, if we have the functional dependency for variable x, y, z such that we have x tends to y, z, I can decompose it as x tends to y and x tends to z. The next property is pseudo transitivity. It is a bit important. At sometimes we may require this property quite often. So we have P tends to RQ and we have Q tends to S. Here this Q is repeating, first in the right hand side part, second in the left hand side part. We can do a bit of arrangement and we can write it as P tends to RS. Here just to remember, we are omitting the common attribute and we are just writing the remaining attributes together. So we have P tends to RQ and we have Q tends to S. Together they can be written as P tends to RS. This is called pseudo transitivity. Now the next topic is equivalence of FD or equivalence in functional dependencies. How we will check that two given functional dependencies are equivalent to each other. Here equivalence of functional dependency means to determine whether all the functional dependencies existed for the relation are equal or not. That means one set of dependencies in one relation holds for the another relation as well. So for checking the equivalence, what we do, we take a relation with different functional dependency sets of that relationship and then check whether one functional dependency is subset of the other or not, or both are equal. So in finding the relationship between two sets, we follow these steps. Suppose we have S1 and S2 as two functional dependencies, and for the set of relation capital R, first step is if all the FDs of S1 can be determined from the FDs present in S2, we can say that S1 is subset of S2. That means S1 is a part of S2. Similarly, if all the FDs of S2 can be determined from the FDs of S1, we can say that S2 is a subset of S1. Now by seeing first and second steps, we can conclude that S1 is equal to S2 because it is only possible when both these FDs are equal. Let us take an example. We have two FDs. First S1, which says that the set of FDs are A tends to B, B tends to C, AB tends to D. And second S2, it has functional sets as A tends to B, B tends to C, A tends to C and A tends to D. First step, we will check whether all the FDs of set S1 is present in set S2. Okay, now check. So we have A tends to B in S1. It is also present in S2. We can clearly see that. Second, B tends to C. The B tends to C in set 1 is also present in set 2. Next, AB tends to D. Here directly it is not appearing that AB tends to D, but if we can use different axioms, we can write it in this format. So it can be derived. In the set S2, AB closure is A, B, C and D. That means all the values are there, right? So we can determine ABCD functionally from AB, which implies that AB tends to D holds for S2. So this all the FDs of S1 holds for S2. We can write S1 subset equal S2, not equal, subset, only subset. This property is true. We do it for the other. We try to verify all the FDs of S2 in S1 now for the same problem, checking whether all the FDs of S2 are in S1 or not. First A tends to B, obviously it is given, B tends to C, it is also very evident. Then A tends to C, it is present in S2 but not in S1, but we have to check whether we can derive it or not. If we can derive, we can see that if we take a closure of A plus or A, we have A, B, C and D. That means A, B, C, D can determine functionally from A, which implies that A tends to C also holds. We can say that S2 tends to S1 is true. In the first step, we have seen that S1 is subset of S2. In second step, we have seen S2 as subset of S1. From 1 and 2, we conclude that S1 and S2 are functionally equivalent. Okay. So with this diagram, we can see it once more. So S1 is subset of S2 in the right hand side part. That means it is a part of S2. Similarly, on the left hand side, S2 is subset of S1, that means it is a part of S1, and in the middle with both these numbers it is only possible when they are same. So we conclude that S1 is equal to S2. Let us see and what we have covered in this module. We started with the brief of what functional dependency is. We have covered the attribute closure in functional dependencies. We have seen different axioms of Armstrong's in functional dependency, and we see how equivalence of functional dependency is seen. I hope this session is beneficial for you. Keep learning until the next module. Thank you.